Hi Year 12, so welcome to my first Year 12 chemistry lesson. What I hope to do today is to go through for you and help you to understand the oxidation reaction. So the oxidation reaction is one of the reactions that we looked at in our practical a couple of weeks ago, and I'm going to go through the theory today, and hopefully if there are any misconceptions or misunderstandings or inabilities to understand exactly what the textbook is saying, then hopefully this will put it right. So we're going to be talking about the oxidation of alcohols, and as you know there are three types of alcohol: primary, secondary and tertiary. And we are going to begin by looking at our primary alcohols and what they do when exposed to oxidation. So with the primary alcohols, when they're oxidised, you should have an idea, if you have been reading your textbook, what those turn into. Now remember what I advised: when you're watching my videos, have your hand on pause so that when I pose a question you can pause the video and think, and then press play when you've got an answer in your head. That way you will get feedback just like you might in a lesson if you've been putting your hand up to answer a question. So, primary alcohols, the product of oxidation of primary alcohols, you should know, is an aldehyde. And you need to know what functional group an aldehyde contains. Now, an aldehyde is one of the carbonyl compounds which contain a C double bond O. And because it's an aldehyde, that C double bond O is at the end of a chain. So, at the end of a chain, C double bonded to the oxygen and a hydrogen then attached. If you wanted to write that as a structural formula, the convention is to write CHO. If you were to write COH, it then looks like an alcohol and you would not get the mark for that. So this is when we apply an oxidising agent, and as you should be aware, when we use an oxidising agent in chemistry, most frequently we use an O in square brackets, and that is representing the oxygen atom from the oxidising agent, whatever that might be. So if we look at a specific reaction, let's look at the reaction of ethanol. So ethanol, you should know, CH3, CH2, OH. So it is an example of a primary alcohol. And notice I'm using structural formula here. Really important that wherever possible you try and use structural formulae in your answers, because that way you can show the examiner that you know what you're talking about, and it distinguishes between the various isomers that some of these alcohols will have, and identifies that you are talking about the primary version. Obviously ethanol doesn't have those isomers, but I'm still using the structural formula. So we're going to apply these to an oxidising agent, square bracket O, and that would react and form ethanol. So I've used the structural formula CH3CHO, and you'll notice the name ends in al. Now, one of the key things that you need to watch therefore is that your handwriting is clear. One letter difference, ethanol and ethanal, really important that that is clearly legible to an examiner. Now obviously at the moment that is not balanced. We have too many hydrogens on the left, and we need we've got two oxygens on the left. So if you look carefully, you will see that the missing product is water. Please be careful that with some of these reactions you aren't, sometimes when water isn't involved as a product, some students have a tendency, or when one of the oxygens, they put hydrogen as a product. Remember, there was no bubbling at all in any of those oxidation reactions when we carry those out in our practical. So ethanol forms ethanal plus water. Now we're going to look at the reagents and the conditions and go through some of the colour changes that are applicable to those. So one of the oxidising agents, one that we used the other day, is potassium dichromate. And potassium dichromate has the formula Cr2O7 2-. That's a dichromate ion. You could use the formula with that in a substance, so you could take away the charge and instead have something like K2 Cr2O7, so potassium dichromate. But dichromate on its own would not actually do anything. You might remember that the other thing that was present in the test tubes when you carried out this reaction was a dilute acid. And that is actually used up in the reaction. It is not in this case a catalyst. So one of the ways that you could write that would be to have /H+, or you could give the name of an acid, so sulfuric acid, or in words you could write acidified. So you could say acidified potassium dichromate. Use the ion charges or correct full formula for the substances that you use. Now the question is, what is the relevant colour change for this reaction? Hopefully you can remember that the dichromate was orange. You saw it a matter of moments ago. And the substance that it turns into, which we will look at in just a moment, is green. And you will see questions regularly where they ask you for the colour change, and you should put the starting colour and the finishing colour in that answer to ensure full credit. Now, what I'm going to do is I'm going to give you the full equation, not because I think it likely that you'll be asked to repeat that full equation in an exam answer, but more that if they do use it, which sometimes they do for the balancing for a molar question, a mole question, or just as information about the ions that are responsible for those colours that you're seeing, I'm going to give you that, I'm going to give you an ionic equation for one of these reactions. So I'm going to use the dichromate. And we require hydrogen ions, and I'm going to use ethanol, and the products of that, the organic product of course is ethanal that we're looking at the moment. We're also going to get our water, and the chromate also has to change, and that changes into a chromium 3+ ion. So we now need to balance that, and I'll carefully put the balancing in. You could check it carefully, but it ends up as 8H+, 3 ethanols, 3 ethanals, 7 waters, and 2 chromium ions. So let's talk about the colour changes. We have orange, and our chromium ions are green. So our Cr3+, so chromium in the +3 oxidation state, is green in colour. Now what I'd like you to do now, using your knowledge of when you looked at oxidation states on the other side of the syllabus, I'd like you to think about what the oxidation state of chromium is within the dichromate. Remember, try and pause the video, have a little think, and try and work it out. So the chromium is in the +6 oxidation state in the dichromate. You have 7 oxygens. Remember, 7 is usually 2 minus. Oxygen is usually 2 minus. So that's 7 lots of 2 minus, which is -14. You can see it's got to come out with an overall charge of 2 minus, which leaves us +12 for the chromiums, and there are 2 of them. So each of them is +6. And that is going to the oxidation state of +3 for the chromium ion. And that is showing that obviously our alcohol is oxidising. When something is oxidised, something at the same time has to be reduced, and the chromium is being reduced. So the chromium is lowering in oxidation state, changing from +6 all the way down to +3. When you're looking at what's happening to the alcohol, in this case you can also look at the loss of hydrogen as the definition of oxidation. There are lots of definitions of oxidation. They won't always all be applicable, but those are applicable in this particular case. Now, I must just mention the conditions required, and you might want to go back where you had reagents and conditions, because we talked about the reagents, acidified dichromate, but you also do need to warm it. Now, it's quite important that if you are specified what product you want when you have a primary alcohol, you have to think very carefully about your condition that you state. When we were doing it, we just wanted to get it to oxidise, to prove that it oxidised, and change the colour of the dichromate. If we want it to be just the aldehyde, then there are some very specific conditions that we would need to use. See if you can remember or think what they might be. We only want it to partially oxidise. So the answer is that you would need to distill out the ethanol as it is formed. Because the objective would be, if you don't want it to further oxidise, and I'll talk about that in just a moment, you would need to get it away from the oxidising agent in the flask alongside the ethanol and ethanol. So as it forms, you can have it in a flask and you can distill it off. So remember, with the distillation apparatus, you want the Liebig condenser to come out to the side, like that. Okay, so you'd have, obviously you can put a thermometer in there to monitor the boiling point and set it up like that. But the distillation, so the reagents in here will bubble away, and as the ethanol forms, it has a low enough boiling point that that's going to come out and distill off, and you can collect it over here, thus getting it away from the oxidising agent, which will remain in here and prevent further oxidation. So if you want the aldehyde only, you must distill off the product, and that needs to be written within the conditions. Okay, so what happens if you don't distill it off? So if you were to, for example, reflux and have the Liebig condenser vertically off the flask and reflux that primary alcohol, have a think what might happen. Now, if you do that, you will form the carboxylic acid. So we're going to have a look at writing the equations, or I'd like you to have a look at writing the equations for the formation of the carboxylic acid. So earlier, right at the start, we looked at a specific reaction where we changed a primary alcohol into an aldehyde, and we had the O in square brackets on the left. You might want to rewrite that one out. What I'd then like you to do, and you can pause the video to do this, is I would like you to write an equation for going from ethanal, our first product, through to ethanoic acid. And also underneath that, for good practice, write the equation for changing ethanol into ethanoic acid, all the way from ethanol into ethanoic acid. Remembering it's perfectly fine to use the O in square brackets. So pause the video, have a go, and then I'll go through the answer on the board. So hopefully you've now had a go at working that out for yourselves, and I hope at this point you're not just turning straight to your textbooks to look that up, but actually challenging yourselves to answer it. So earlier on we had our ethanol reacting with our oxidising agent and forming ethanal plus water. We now want to, the first one I asked you to do, which was new, was to go from ethanal, so starting at ethanal, remember CHO, oxidising, so we're going to require some more oxidising agent. And we know that our next product of oxidation of a primary alcohol, if we completely oxidise it, turns into a carboxylic acid. So the relevant carboxylic acid, 2 carbons in chain length, is going to be ethanoic acid. Now you can see here 2 carbons, 4 hydrogens, 4 on the left, 2 oxygens and 2 oxygens. You can also see it's oxidation, you've got gain of oxygen here, you've also got just gain of oxygen from that reaction. Now the second one I asked you to do was to go starting from ethanol, which is CH3CH2OH, and oxidise it, but this time write it as if you're not stopping at the aldehyde but going all the way through to the carboxylic acid. And what you'll see there is you've now got too many hydrogens on the left, and that tells you, and this is where you've got to be careful, because some of you might look and say, oh, 6 hydrogens and I've got 4 over here, and you might think 2 oxygens, you might think it was balanced with hydrogen. Remember, no hydrogen product, doesn't bubble. What we're looking for is our water. And then what we need to do, we've now got an extra oxygen, and what you need to do is put a balancing 2 in front of that oxygen there. So you can balance in front of this O in square brackets exactly the same way as any other reagent. Okay, so that is your full equation. Now if you see, what we've got here is this is the sum of those 2 reactions together. So here, this one is forming ethanol, and this one is using ethanol. And so if you look, you've got ethanol there, 2 oxygens in square brackets, carboxylic acid, and water. And so that makes sense that this is just these 2 reactions happening consecutively all in one go. And in order to make that happen, if they want you to make the carboxylic acid, and they've required you to do that, then you need to make sure you use the condition reflux. Remembering, you should be able to answer what reflux means. So reflux is a continuous process of evaporation followed by condensation. So every time it evaporates, it will drop back down into the flask. Given another chance to react further with the oxidising agent, any of it evaporates, whether it be product or reagent, then it will drop back down, and gradually you will increase the yield, and gradually you will push your primary alcohol to fully oxidise all the way to the carboxylic acid. So I'm just going to clear the board. Now do remember, with those processes of distillation and reflux, you also need to be able to recognise those from given diagrams. So the diagram I drew on the board earlier of distillation with the Liebig out to the side, and the diagram which we've seen in a previous lesson with the Liebig vertically from the flask, you should recognise that's reflux, because depending on which diagram they were would depend on the product that you would get when oxidising a primary alcohol. Now, just for information, the balanced equation, full balanced equation for going ethanol with dichromate, which we'd require 2, and 16, I'm just going to squeeze that down there to make sure I don't run out of room, 16H plus. If we reflux that, then we will get 3 lots of our carboxylic acid, 4 lots of our chromium 3 plus. Identical product in terms of our chromium, and again I'll just drop it down to the next line, 11 lots of water. So the balancing is different because we're using more oxidation state because we are oxidising it further. Obviously our organic product is different, but our chromium ion is the same, and so our colour change does not change at all. You're just changing more of the dichromate into the chromium ion. So the colour change, whether it be to aldehyde or to carboxylic acid, is identical. Orange through to green. Now that is the oxidising agent that you've met. You met in a practical, giving them a kind of aid to memorise that, and having seen the colours for yourself in practice. But there is an alternative. Now obviously if you're just suggesting an oxidising agent, then acidified, don't forget to put the acidified dichromate is perfectly fine to use. However, you do need to be aware of another alternative oxidising agent which they could pose in a question, and you'd need to recognise that that's what it was so that you could work out the product accordingly. So another oxidising agent that is possible to use is acidified, again it's acidified potassium manganate 7, or manganate 7 ions in the presence of acid. So an alternative oxidising agent is, so we can use KMNO4, so give a specific with acid, you can just use H+, or you could instead use MNO4-, that means the same thing, it's just manganate ions. Again, you must say acidified, will not work without, so you wouldn't get the mark, certainly not full marks, if you just talked about using the manganate 7 solution. And here, the manganese oxidation state, you could have a little think about what it is. The clue is, if you do know the sort of modern name for that, the clue is there. It is 7, okay, and that you can work out and prove again. You've got 4 lots of oxygen, each at 2-, but an overall charge of 1-. So that means that each manganese, there is only one here, is +7. Okay, so manganese is in the +7 oxidation state in the manganate ion. And in the equation, which I'll just create room for, so again, I wouldn't expect you to be able to recall, or even certainly at this stage work this out, but just in case I give it to you in an exam, it's not going to scare you off. You've got to have that acid, it's used up, we require 6 moles of that acid, H+ ion, 5 lots of ethanol will be oxidised to, and the manganese goes to the Mn2+, manganese 2+ ion, 8 lots of water are formed, and that is for the go down to the next line just to squeeze it in. That is for the formation of the aldehyde again. Now, the one thing you need to know about this, just in case you either choose to use it because that's the one you remember, or if they've given you the oxidising agent, they ask you a question about the colour change, you need to know what that is. So this is the solution. Just hold it close to the camera. You can see there potassium manganate 7. You've probably seen that previously in your chemistry and used that. Sometimes we use it in diffusion experiments. The colour of that is purple. It's quite a dark colour, so that's why I've swirled it around the tube. So that the ion responsible for that purple colour is the manganese ion, and the manganese ion, the Mn2 plus ion, is we normally say colourless. In fact, it's very pale pink, but in all likelihood you may not notice that pale pink colour depending on the concentration of the solution, and it would be acceptable and usual, in fact, to write the colour change as purple to colourless for the colour change using that oxidising agent. Okay, so that is the oxidation of primary alcohols. So now we're going to go through the oxidation of secondary alcohols and make sure you're happy with that. Now, the good thing is that all of that information that I've given you about reagents, conditions, or colour changes, oxidation state of those various things, that is all going to be the same. So you don't have to use a different oxidising agent just because you're using a secondary alcohol. So if you remember, a secondary alcohol has two R groups. Remember, we can use perhaps R and R dash because they don't have to be the same, attached to the carbon that has the OH on it. So just put it on the side like this. Doesn't have to be like that. And if we have our oxidising agent again, what happens with this is you turn it into, have a think, see if you can remember from when you wrote up your practical, have a think about what the compound type, the functional group is of the compounds we get from oxidising secondary alcohols. The answer is ketones. And a ketone is another example of a carbonyl compound with a C double bond O. And just to reflect what I put on the left, got R and R dash. And again, to make that balance, we require the water. So this is a ketone. Note the spelling of ketones, no Y in ketone, K-E-T-O-N-E. And the names of those end in -one. So if I were to use a specific alcohol, I'll put the R groups, both R groups, as CH3. Remember, it's good practice to join the bonds through the carbon, so that is correctly represented with the oxidising agent, and that will form, draw it out in the same way, just try and correct like that, and that you can see then we've got our 3 carbons in a row. What makes it a ketone is that the C double bond O is in the centre of a chain or in the middle of a chain, not on the end, and that name then becomes propanone. So the ending -one, and remember we need our H2O, our water, just to finish that off. Now, unlike our primary alcohols, ketones will not further oxidise. If you think about what happened with an aldehyde when you had a C double bond O, remember one of these was an H, and when it oxidised further, you had an aldehyde turning into a carboxylic acid. Now here, the carboxylic acid. Now here, for a ketone, we've actually got another R group. Let's put in a CH3, for example. Now, if I were going to turn that into something like a carboxylic acid and try and add in more oxygen, you'd actually need to use this bond to join that OH. And that would involve the breaking of that bond, and that bond is really strong. So that is not going to break. And that is why ketones do not further oxidise. So you do not get a ketone further oxidising. So there's only one answer. So as far as you're concerned, you can use reflux right from the start, and you will then get a good yield of the ketone. So that is secondary alcohols. So our final alcohol set is the tertiary alcohol. And with the tertiary alcohol, we have, of course, 3 R groups attached to our C with the OH on it. Now the thing about this is we have the OH, and with all the others we've been turning it into a double bond O. If you had to turn that into a double bond O, that would mean there would need to be 5 bonds, or we'd need to get rid of one of those. So again, we have this big issue, and this is why it doesn't oxidise. We would have to break off one of those carbon containing groups, one of those R groups. So the reason that we would give if we were asked why tertiary alcohols don't further oxidise is that that reaction would require a strong carbon-to-carbon bond to be broken. And that energy is not going to be there. That is not going to be energetically favourable for that to happen. Okay, I'm going to stop this video now, and I'm going to do a separate video for our next topic of the organic chemistry.